Hello, so today is day 23. What we are going to be doing is that we're going to be talking about standing waves, and specifically, we're going to try to do a standing waves lab together. So, here's kind of our agenda for the day. What I'm going to do is that I'm going to actually be talking less today, and I want you to be doing something and interacting more. So, I'm going to start out with just what is a standing wave, kind of what is resonance, things of that nature. It's very, very important concepts inside of our waves unit. Then we're going to try and do a standing waves lab together. I'll get you started. I'll figure out all of the different variables with you, make sure that all of your settings are right. And then afterwards, hopefully you can draw some big conclusions based off that lab. And I can go into the application and usage of standing waves and then resonance. Now, homework-wise, you know that due this Friday is going to be your Speed of Waves lab with your conclusion section with it. There's the assignment tab in Canvas where you can go and you can turn it in right there. And then hopefully by the end of next week, because I know that next week is a shorter week anyway, I am hoping for your Standing Waves lab. Again, there's going to be an assignment tab on Canvas in which you can turn it in. And then you are going to have some wave practice problems. These are the ones that I was trying to hand you before break. But now, especially since we're going to have standing waves after today, they're going to be a lot nicer for you to do. And I hope that, we can do them at least a little bit together next time. So here's our agenda. Let's go ahead and let's get started. So what is a standing wave? First off, let me give you the definition, and then I'm going to draw one with you when we're trying to figure out exactly what it is. So a standing wave is something in physics. You know that there's types of constructive and destructive just interference. And a standing wave is a perfect example of constructive and destructive interference happening at the same or at the exact same time. And what it does is it creates a resonating object. So let me show you kind of what that looks like. So what we want to do is that if I first just draw a wave for you, let's make sure I can do this right. Keep on going. So, with your wave, this is a wave. And most of the time with a wave, if it hits an object of some sort, then that wave, especially if it's a closed end, which is exactly what you're going to be working on, it's going to reflect along this x-axis. So your wave then is going to come back onto itself and just make a bunch of like infinity patterns over and over and over. And that's a horrible wave, but you see that you have spots of constructive interference here and then spots of destructive interference here, because this is perfectly out of phase. You notice it's going up towards a crest here for this first wave, and then it's going down towards a trough on the second wave. This is a perfect destructive interference at this point here. And then here is perfect constructive. You are going to have a maximum amplitude at that point because of it. So what you have is that this is a standing wave, as horribly drawn as it is. The standing wave is literally just a wave that goes and bounces off of some type of object, usually a closed end, and then reflects perfectly back upon itself. And it creates what is something called a node and an antinode. So a node, think of it, are the spots in which there is perfect destructive interference. So if I get my pen and I try and change my color, let's do a nice, I don't know, cyan. That this right here is a node, this spot, wherever there is perfect destructive. And perfect constructive is an antinode after everything is said and done. So these are the two parts of a standing wave in which you need to know. This standing wave specifically has, you can tell, 1, 2, 3 nodes and 1, 2, 3, 4 antinodes for this wave. Now, I set a word up here, and that is resonating object. Do you know what a resonance is, or like a resonating frequency? Let's first go through that idea, and we'll go from there. So let's start out. Resonance is whenever the amplitude of a wave is being increased by its resonating frequency. What I mean by that is that, again, look on this specific GIF. You notice that this wave traveling this direction is going to have points of perfect constructive right here, and then destructive interference, say like right here. Notice how this section of the wave, specifically that spot, does not move very much. That this purple wave that you have created, this is a standing wave. And it's called a standing wave because there's points on the wave, specifically the nodes on the wave, that appear as if they stand still. So you have points of large antinodes and then points of nodes after everything else is said and done. Now with this, resonance again is whenever this amplitude is increased. It's only because this wave matches perfectly with the yellow wave here traveling that you have a resonating object and you have a standing wave being created. That it's if these two waves, like this gray wave traveling this direction and then this yellow wave traveling the other way, were not perfectly in phase, there would be no resonance. So a lot of the time resonance you hear in terms of like music. So if you want to look at like that side, like piano behind me, or like the guitar that's next to it, all of those have just resonant frequencies, and you'll start hearing them in tunes and stuff of that nature. If you hit like a metal table as opposed to like a wooden table, again, you're going to hear resonance. But we need to talk about harmonics. So a harmonic is like a harmony. Every single time in choir you are singing in specific harmonics, you're trying to match your wave to what is the resonant frequency of that sound. So in standing waves, we always say that the wave is harmonic in, and in just represents an integer here, so like 1, 2, 3, 4. They can never ever be decimals, but you'll see that in a second. And it's always based off the number of antinodes. Again, it has to be antinodes for it, not nodes. So I just copied this GIF down below too, because I want us to go through and I want to figure out which harmonic this standing wave is moving in. So what we're going to do first is that I like to go and I like to count first the nodes. Now, nodes at the front and at the end of the wave do not count. These are just reflection points for this wave. Think of it, it could be like a ring stand over on the side here or over on the side here. That specifically the nodes are right in the middle here. So we have 1, 2, 3, 4 nodes specifically on this standing wave. And then our antinodes, we would have 1 here, 2 here, 3 here, 4, and then 5. Remember, an antinode is wherever you have the highest amplitude. I always like to think of them because they are matching A's, amplitude, antinode. So if we have 5 antinodes, this standing wave then would be our 5th harmonic. And that makes it so much nicer for all of us to go and say that it's the 5th resonant frequency for this specific wave. So what we are going to do is that this is your lab. It is time for you to determine what the harmonic of a standing wave is dependent on. So let's go and do this together for a bit. I'm going to try and close out here. I'm going to keep those. I can do that later. And let's go to our extra 2. So off to the side here, let me start out just over here. This is your lab, specifically that you are going to be doing. What I want you to do is I want you to read the starting portion, and then you are going to start out your lab here. And it says, to begin, start by measuring the length of your string on the program. So the program is right here. It's the PhET simulation that we were going and we were using last time. Let me first move me down to the bottom. And we can talk about your settings. What you want to do first is that you are going to be using the oscillate function, not the manual, because the manual makes you do it and your frequency is going to be however many times you go up and down. So you want oscillate at a specific frequency. You want to go to the fixed end here to make sure that it has 2 points of reflection. That way they can bounce back and back and back, and you can start creating standing waves. So I'm going to measure the length of my string first, just saying however long my string is from the very, very center here all the way over to this side. So you notice for me, it's about 1, 2, 3, 4, 5, 6, 7. This is 7.4, 7.43 centimeters is probably what I would go and I would write here for the length of my string. So I would do 7.43 centimeters. Now, or just other variables that this program wants you to follow is that it wants the amplitude set. Let me move up here. That's fine. So the amplitude it wants set to 10 centimeters, which is fine. And high tension, got it, and then zero damping. And damping is just how much it actually goes and it resets. Now, right now, even you can see this is a standing wave. If I go and I just set it to normal speed and I start moving through the frequencies, you're going to start getting frequencies. Let's just restart it. Of which that wave is going to come and it's going to transpose back upon itself. Now, this is a really, really close to a standing wave, but it's not perfect. And what you are going to do is that you are going to try to create 7 different types of harmonics. And you are going to tell me the number of nodes, antinodes, and then the frequency. For this wavelength and the velocity, these are going to be using these 2 equations of either your velocity is your wavelength times your frequency, or to find the wavelength, it's 2 times the length here, the 7.43 centimeters, divided by n. And n is just your number of harmonics. So let's try and find a couple of different harmonics together first. What you notice is that starting out here, this is almost a harmonic, but a really, really good way to tell a harmonic is, well, actually 2. The first thing that you want to do is that you notice whenever I start and I just let it run, that it's going to start going, and then eventually it's going to like die out. And that's a problem because you know then that that frequency is not perfect. Notice how it dies right there. That's not a perfect frequency, meaning that you're not at a resonant frequency and you're not on a harmonic yet. But let's just go through some, and I can press restart as many times as I want to try and figure out. Now, this is almost a standing wave, but remember what a standing wave wants to do. It wants to create a resonance. Ooh, that's almost really, really good. And what a resonance is that a resonance by itself creates the highest amplitude. So something that you could do is that you could get this like reference line over on the side here, and you could see wherever it creates the highest amplitude. So I would let this go and travel, and I could mark the highest amplitude where I think that it is, and then I can start changing the frequency. And if I start changing the frequency and then it creates a higher amplitude, then I know that that's going to be closer to my harmonic frequency than the original. So here, this 1.60, you notice this amplitude is not getting close to that red line that my 1.62 hertz had. So then I know that 1.62 is closer to the harmonic frequency than that 1.60. And again, I would just go through and I would say, okay, how can I get the best ooh, that's actually pretty good, right about there. And you notice it's because the amplitude is going higher, that it's going to die out. It's not perfect, but that's okay. Again, it's a lab. You're not going to get everything perfect. But especially if I go into slow motion, do you notice how there's these points here, my nodes, that really are not moving very much from this equilibrium line? These nodes are moving a tiny, tiny bit, but instead this is a standing wave, and you can tell that specifically based off of what you have. So now let me do this. Let me pause on whenever we have the highest amplitude. Oh, it didn't really work that one. Let me pause whenever we have the highest amplitude, and then we can go and we can fill out parts of this data table together. So I'm going to give it a second. There we go. Okay. So what you notice right here is that let's first go through the number of nodes, number of antinodes, and then my frequency together. My number of nodes, remember, are just points in which they are still across the equilibrium that do not move. So if I want to count my number of nodes, I have 1 here, 1 here, and 1 here. I have 3 specific nodes for this standing wave. So I would go and I would write my number of nodes for 3. Then antinodes. My antinodes, I have 1 here, again, highest amplitude possible, 2, 3, and then 4 over on the side. So you have to start thinking, if it's 4 antinodes, then my number of nodes, I did not create the first harmonic. I went and 4 antinodes is going to be the 4th harmonic. So I would then write, let me get rid of that 3, and I would say 3 nodes and 4 antinodes for this specific harmonic. And then my frequency would be 1.64 hertz. Then, I would just go and I would start trying to find a different harmonic. So I would set play again and I would start changing my frequency. Let's go down to just like 1. And let's see what 1 has for me. So I'm going to restart, play it back into normal speed, and wait. Now, do you think that this is a standing wave? Even right here, it's kind of not really creating a large amplitude. A standing wave is going to have a very, very large amplitude. And you notice how even here, like the wave itself dies down over time. So this frequency, I'm not even close to a standing wave yet. I have to really start changing and playing with that frequency. Let's try 1.1 and then restart and see if that's something. And ooh, it's getting there, but it's not great. Now, the reason why I said it's getting there is because, again, you notice there's these points of high, and then almost nothing, and then high, and then almost nothing. Again, I'm close. Let's try 1.15 then, and then restart. And this is just going to have to kind of be the setup that you do. That's not bad, but do you notice my reference line? Do you notice how small that amplitude is to my reference line? Again, I'm not quite there. Let me do 1.20. Again, restart and just kind of let it wait. It's not bad. It's definitely getting better. And again, I would just kind of change a little bit at a time, restart every single time, trying to find that specific harmonic. So if I do 1.23, what do you think? It's going past my reference line. That's a pretty good standing wave. Again, it's a large, very large amplitude. I would say that's almost perfect. So then again, let me just pause it and we can try and figure out the number of nodes and antinodes together. So again, I have one spot here that's not moving. I have another here that's not moving. Then I have 3 perfect spots of reflection. It's literally that my wave is going and it's moving and it's reflecting back perfectly to create this standing portion. So if I count the number of antinodes, I have 1 over on the side here, 1 over here, and 1 here. And 3 antinodes will always tell me my harmonic. So I have then 3 antinodes for a third harmonic. If I count the number of nodes, I have 1 non-moving here and 1 non-moving in this spot. So I have 2 nodes, 3 antinodes, and then my frequency is 1.23 hertz. This is how you're going to complete your lab. I want you to go through this entire data table and try and find each harmonic. Now, I will tell you that the smaller the harmonic that you go, the more difficult it is going to be. And you really, really have to be absolute and very, very precise with those data in order to figure it out. Then, at the end, let me just blow this up again. I'm going to want you to go through and just answer a couple of questions for me. It says, specifically, it's talking about a fundamental frequency. Every single object in the fundamental frequency is going to have just as the first harmonic. And I want you to practice and to predict some things. So I'm going to see how accurate you are with your harmonics by going and dividing the frequency of your 4th harmonic divided by the frequency of your fundamental. Or I'm going to have you predict, talk about some errors, and then finally try one problem. So the way in which you're going to do your lab is just that. You can either type out, like you see I'm drawing right now, and you don't have to do that, but specifically you could like type out for this section, or you can print it, take a photo of it, whatever in the world is best for you that creates a lab that you are able to complete. I am perfectly okay with. So either way here, that's going to be your lab, and it has some big, big ideas. So at this time, what I'm going to do is I'm going to say pause the video. Right now, pause the video, go and complete the majority of this lab, or at least as far as you think, and then come on back, okay? So I'm going to give you a 5-second buffer of just pause. 1, 2. Okay, so now let's figure out what in the world you were trying to actually do with your lab. So with your lab, first off, let's do it this way. You should have figured out, again, the speed of a wave is not dependent on the medium itself. Your velocities for that lab should have been the exact same all the way down. That's one way in which you can tell whether or not your lab is really, really accurate. And of course, they're not going to be the same. It's a computer program, for goodness sake, so it's not going to be perfect. But you could get really, really close with it. So that's your starting point. And I want to talk a little bit about how do we use these types of like standing waves? What's the purpose? Why are we talking about resonance? Well, first off, let's go here. That really any object that is met with a resonance is going to create the greatest amplitude. And you've seen things like this before. So down here over on the side, this is a famous, famous, famous bridge in like Oregon, I think, in which it was a very, very windy day. And you can see that this wind is going and it's matching this resonant frequency of this bridge. And it's creating a standing wave along this specific section. And eventually this bridge did just like snap and did break, and thankfully, of course, nobody, like in the video you can see there's like cars parked over here and over on the side, but nobody's in this middle section, so nobody was hurt. But it's a really, really good example of just resonance in natural objects. Or you've probably seen at some point in time like someone trying to break a wine glass with like their voice, and what they do is they go and they tap that wine glass and then they try and listen, and they're listening to that fundamental frequency. So they go and they match that fundamental frequency, and you can see this is a great amplitude enough until which the stress of that amplitude is overcoming the structure of that wine glass, meaning that it's just going to shatter. So you're matching the natural frequency. And you go and you talk to me and you're like, okay, Mr. Tate, how in the world do you find a natural frequency? Well, the honest and simple conclusion is that you just add energy to something and you figure out where this greatest amplitude is. So both of these gifts down here, these are called Chladni plates, and it's just Chladni, Chladni plates. And what they are is that you take a piece of metal and you go and you pump a frequency through it. So like here, this is 345 hertz. And what it will show is that it will show the design. This is literally the stress points of this plate and a high and a low frequency. So over here, again, this person is going and he is vibrating this plate with just a violin bow. And there's just sand. I think it's like salt over on this. I've done it with salt before on this side, but this is just very, very fine sand. And notice where he's holding, because he's holding a specific node on this plate. And you notice how that goes and creates a line right there. It's because of the fundamental frequency of this object. So he's going and he's sending energy, and you get these really, really cool designs. It's not like the plate itself is made for it. It's the same exact plate. It's just a metal thing. But they're sending energy through it, and then they're finding the resonant frequency because of it. So you're going and probably thinking, okay, Mr. Tate, where in the world do we use this? And you have to realize we use it every single day. You going and listening to me right now, you are using resonant frequencies. That my frequency of my voice is changing and it's undulating that pitch so much that you know and you recognize it as words. Or if you are a musician, you know that each one of these, such as like a violin, you can see, or a guitar, these are standing waves being created on those strings. If you want to talk about what a fret of a guitar is, even right here, that's a node. It's a point in which specifically that energy is traveling, and there's a point of zero energy because it's a standing wave. So you use specific and resonant frequencies all the time. You might not think it, but your eyes match resonant frequencies. You can see blue, green, red. You can tell whether or not the sun is high and hot in the middle of the day because of that frequency. All of this is resonance, and you use it every single stinking day. So it really is this cool, fascinating type of like structure. And I wish I could show you some of these really, really cool demonstrations with it. But any of these, you're going and you're learning exactly what resonance and what this resonant frequency is based off of standing waves. So that's the main idea. And we're going to hit resonance and resonant frequencies even more. Let's talk about where we're going. Next, what we're going to be doing is that you are going to have a homework, again, of just practice problems. And I think I'm going to put them on formative this time, of just electromagnetic wave. And what we are going to do is that I'm going to just go and ask you, and we're going to practice a couple of these probably at the start of class next time. So I'm going to do a couple of them together with you, but I want you to take a look first. And then also next time, we are going to start moving into the electromagnetic spectrum. Sound is something that we've been working with a lot as a type of energy, but it's one of many. Light is the really, really big one. It's how you can go and see me or interact with me even right now. So we need to talk a little bit about the electromagnetic spectrum and then optics after that. But as always, thank you all. I really do miss you all. I'm having more and more fun making these because it still gives me some sort of interaction. But don't remember, every Tuesday, Thursday, 11:15 to noon, I'll be on Zoom. Please let me know if you have any questions. Everyone, stay safe. Thank you.